Okay, so the next speaker is Alexander, and he's going to explain us a better than 3n circuit lower bound for an explicit function.
Thank you for the introduction. Yeah, my name is Sasha Glavnev, and I want to present a new circuit lower bound, which is a joint work with Magnus Fint, Edward Hirsch, and Valery Kulikov. The main question in this line of research is to prove lower bounds on computations. And the simplest computation model is so-called straight line program. Think that all your variables are Boolean variables, then straight line program is just a program with no if statements, with no branching. And it naturally corresponds to a Boolean circuit. And formally speaking, this is a circuit where you have n Boolean inputs. You also have constants 0 and 1 for free. And each gate can compute an arbitrary binary Boolean function. So we do not pose any restrictions on fan-outs nor on depths. So again, all fan-ins are 2, and fan-outs and depths are unbounded. Already in 1949, Shannon proved that almost all Boolean functions require circuits of exponential size. Later, Lupanov showed that the tight upper bound, that every function can be computed by a circuit of size like 2 to the n over n. But the main challenge here is to prove a lower bound for an explicit function. That is, for a function from a reasonable complexity class, like NP or P, something like that. So here's the list of known explicit lower bounds. Kloss and Malushev in the 60s proved that symmetric polynomial of degree 2 cannot be computed by a circuit of size smaller than 2n. Then Schnorr proved essentially the same bound for the mod 3 function. Paul in 1977 proved that the so-called indexing function cannot be computed by a circuit of size 2.5. And here you should think of X as a bit string of length n, and A and B as bit strings of length log n. Then you just take X sub A and XOR it with X sub B. Then Stockmeyer proved the same lower bound for almost all symmetric functions. And finally, Blum in 1984 proved a lower bound of 3n for a slight modification of the indexing function. 5 years ago, Demenkov and Kulikov proved essentially the same bound, but for a very complicated function called affine disperser. And now we slightly improved this bound for affine dispersers. But still, I want to say, we're like children playing in sandbox. Our goal is to prove super polynomial bounds, or at least like super linear bounds, and this is the best what we can do. And I want to quote here Saxena and Seshandri, their work on depth 3 circuits, but this is relevant to our model too. They say like, this question is still open. This may seem depressing. Well, it is. And just to show you a plot of the known lower bounds, like from 60s we know a lower bound of 2, and from 70s we know a lower bound of 2.5, and then from 80s, 3n, and this is like our latest achievement. So essentially, the only method we know, the only method we use in proving lower bounds in this unrestricted depth model is gate elimination. And gate elimination normally has 3 steps. Say you want to prove a lower bound of 3n. You fix some class capital F of functions, and that's what you normally do. You say that for any circuit that computes a function from this class, you can find some substitution. Say you can substitute a constant to a variable such that you can eliminate at least 3 gates from the circuit. Like your new function, your new circuit won't need the 3 gates to compute the new functions. Then ideally, you would say that your new function, which probably depends on n-1 variables, still belongs to your class. And then you can say, okay, then I can repeat the steps because I'm still in the same class. And if you do it almost n times, each time eliminating 3 gates, then total you eliminate almost 3n gates. Thus your original circuit was of size at least 3n. Here's an example of gate elimination. Say I want to assign 1 to x1. Then G5 would compute just negation of G3. So I don't need this gate G3 in my G5 in my circuit anymore. I just can feed G6 by negation of G3. And to make it a normal circuit without any like negations on the wires, I can just flip a bit here. I mean, change the function in computing in G6. Okay, but ideally to prove even like 3n lower bound, I would like to eliminate 3 gates. That's how it normally works. One more example. I assign 0 to x3, then again G1 computes just x2, so I can eliminate G1. And also I feed G2 by 0. So this n becomes 0, and it also kills the next gate because it's fed by constant. So I succeed, I eliminate 3 gates. Unfortunately, it's not always possible to eliminate 3 gates using this kind of substitutions. What is possible, what is easy to show, is that if I could make more general substitutions, if I could substitute linear functions instead of constants to my variables, then I could actually easily eliminate 3 gates each time. But what function would this lower bound be for? This leads us to the definition of affine disperser. So affine disperser is a Boolean function that affine disperser for dimension d is a Boolean function that is not constant on any affine subspace of dimension at least d. Equivalently, you can say that affine disperser does not become constant after any set of n minus d consistent linear restrictions. And this is exactly what we wanted, like on the previous side. We wanted to make linear restrictions rather than just constant restrictions. And luckily, affine dispersers let us do it. It is known that the class P contains affine dispersers for sublinear dimensions. The first construction was obtained by Ben Sasson and Caparzi a few years ago. So this slide just says that actually we can easily prove a lower bound of 3n minus little of n. Indeed, we can each time eliminate 3 gates, making an affine substitution, and there exists a function in P that does not become constant after almost n substitutions of this form. But it also can be shown that using this idea, you cannot prove a stronger bound. You cannot improve the lower bound of 3n minus little of n. So we have to use some new ideas, some new techniques to prove a stronger lower bound. So our goal is to prove a lower bound of 3.01n for the same function for affine disperser. Here are the 3 main techniques that we use. I will discuss them briefly in the next slides. So the first one is delayed linear substitution. The second one is cyclic circuits, and we also introduced quite complicated circuit complexity measure. So the first one, delayed linear substitutions. Again, it's not enough just to make standard like constant substitutions or even linear substitutions to variables. So sometimes we also make these quadratic substitutions. But each time when we make it, we guarantee that by the end of the gate elimination process, we will substitute one of these like quadratic variables by a constant, which will turn the quadratic substitution into a normal linear restriction. So we guarantee that in the end, we will have only linear restrictions. But in the process, we will sometimes make quadratic substitutions. The second new ingredient of our proof is cyclic circuits. In our proof, we don't know how to stay in the class of normal circuits. So we have to allow for some cycles. But in general, cyclic circuits can be quite messy. It's not even clear how to evaluate such a circuit. So we allow only for very nice cycles. First of all, we say that every cycle in our circuit contains only XORs, only linear gates. And the second restriction is that if you write a linear system for your cyclic circuit, then the corresponding matrix has full rank. This means that for each assignment to the variables, you have a unique assignment to the gates. So this means the circuit is nice. You can actually evaluate it, just not in a regular way. You can evaluate it by solving some linear system. Okay, and the last ingredient we used in our proof was a carefully chosen circuit complexity measure. I mean, ignore the constants. This is just solution to some linear program. So what we want to say to improve this lower bound of 3n is we want to eliminate more than 3 gates each time, or on average. But we cannot eliminate 4 gates. So we need to keep track of, we want to say that if we eliminate 3 gates, then we at least make circuit nicer in some other way. So for this way, we keep track of 4 parameters in our gate elimination. proof. We count the number of inputs the function depends on, the number of gates, the number of these temporary quadratic substitutions that will make linear by the end of our proof, and also the number of bottleneck gates, where bottleneck gate is a specific configuration that annoys us the most during gate elimination. This is a configuration when we cannot eliminate more than 3 gates. But what is good about bottleneck gate is that when you eliminate bottleneck gate, you at least eliminate bottleneck gate. So you decrease the complexity measure at least by this much. And the constants are just solution to some linear program. It's not like we were trying to guess constants. Okay, this is the 3 main ingredients that let us prove a slightly stronger lower bound. So I just want to conclude with one slide on follow-up works. So in this work, we show that affine dispersers can prove slightly stronger lower bound. Then we also know that quadratic dispersers would give a very simple proof of 3.1 and lower bound. But unfortunately, we don't know explicit constructions of quadratic dispersers. We don't know if they belong to NP, for example. If we take even stronger dispersers, like dispersers for restrictions of large constant or even polynomial degrees, then this would prove even superlinear lower bounds in some weaker models, like series parallel circuits or circuits of log depth. And the natural question to ask is if, would strong, like really strong dispersers allow us to prove a superlinear lower bound in this general model? And unfortunately, the answer is no. Now we know that even if you have like incredibly strong disperser, you cannot hope to prove even a lower bound of 5n. Okay, so to conclude, these techniques allowed us to improve a lower bound of 3n by a little bit. Now we know that these methods will never lead to a lower bound even of 5n, and this means that this line of research really needs new techniques. I just wanted to thank you for your attention.
Okay, so any questions?
Yeah, we can show that if you use gate elimination, as we know it now, then even if you have like extremely strong disperser for equations of polynomial degree, still you cannot even prove lower bound of 5n. We can construct a function such that whatever substitutions you make, like you can always eliminate at most 5 gates. So this gate elimination, as we know it now, I cannot prove this lower bound even for very strong dispersers.
So you said that for log depth linear size circuits, you can get lower bound for high degree dispersers?
If we had if we have a disperser of for really high degree, then this immediately applies a superlinear lower bound.
So would that mean that, let's say, you can separate NP from linear size log depth?
I mean, if we had these dispersers in NP.
So you don't even know that it's an
We don't even know if quadratic dispersers are in NP yet.
No, I'm not talking about C, NP.
NP, yeah.
And sigma 2?
No, I don't know. Sigma 2x, for sure. But yeah, sure.
Are they fine circuits between nodes?
Sorry, I can hear you.
Are they affine circuits between nodes?
Yeah, they're in P. Yeah. Yeah.
How high degree would you need to handle to get the superlinear lower bound for log depth?
For log depths, you need polynomial degrees, like n to the epsilon. For superlinear lower bound against series parallel circuit, it's enough to have dispersers for large constant degree.
What kind of entropy do you want for quadratic dispersers?
Sorry?
What kind of entropy do you have to handle for quadratic dispersers?
That depends. Oh, for quadratic dispersers, we need almost any little O of n would work. Any other questions?
Can you explain where the 3 gates come from? Like, why is the 3 the magic number?
Oh, yeah, just like when you look at this gate elimination, this is the best you can do. I mean, this is the ideal situation when you can assign something and you kill one gate, like, and the other gate with the gate pulls it, and that's it. Like, I mean, yeah, when you look at a circuit of Fanon 2, it's not clear how to eliminate more than these 3 gates, yeah. Even 3 is hard if you don't know linear substitutions, yeah, if you don't use linear substitution.
Okay, any other questions? So let's try this figure again.